5.4 Elementary Reactions. Topic Overview. An elementary reaction is a single step within an entire reaction mechanism. Consider this reaction. Nitrogen monoxide and oxygen gas combine to form nitrogen dioxide. This reaction requires three particles to collide at the same place, same time, in the correct orientation, and with sufficient energy. This is extremely unlikely in the real world. This reaction actually takes place in two steps, or there are two elementary reactions when nitrogen dioxide is produced. First, two molecules of NO react to form an unstable intermediate, meaning the compound is formed and then consumed during the reaction. Then, the N2O2 intermediate reacts with O2 to form the final product. The net equation above is formed by combining both elementary equations and cancelling the intermediates. Note that the sum of the elementary steps must be the same as the overall balanced equation. The molecularity of the reaction describes the number of molecules that must collide in an elementary step. Both elementary steps are bimolecular because they have two colliding molecules. Unimolecular reactions involve only one particle. These might be decomposition, nuclear decay, or isomerization. Termolecular reactions involve three colliding particles. They are very rare because it is highly unlikely for three particles to collide simultaneously in the correct orientations. You can know how difficult this is if you have ever attempted the three-person high five. The rate law can be inferred from an elementary step based on the number of molecules that must collide. In the reaction outlined above, the rate law for the first step would be rate equals K times the concentration of NO squared. Since there are two particles of NO that must collide, this elementary reaction would be second order. The rate law for the second step would be rate equals K times the concentration of N2O2 times the concentration of O2. Two particles must also collide here, so this elementary reaction is also second order. The rate determining step. Sometimes, you are given information about the speed of the elementary steps in a reaction. The slowest step is known as the rate determining step, because it limits how fast the reaction can go. Imagine that you work at a chocolate shop. It takes 15 minutes to make the chocolate, 8 hours for it to cool, and 5 minutes to box the chocolate. In this example, the cooling of the chocolate is the rate determining step, which limits how fast you can make the chocolate. Speeding up either of the other steps wouldn't significantly change how quickly you can prepare the chocolate. The slowest elementary step of a chemical reaction determines the rate of the reaction. If the first step is the slowest, then the overall rate of the reaction will be based on the stoichiometry of the first elementary reaction. If a subsequent elementary reaction is slowest, then all the reactants up to the slowest step are added together and any intermediates are cancelled to determine the rate of the reaction. Topic 5.9 talks in more detail about when the rate determining step is not the first step.